Hello students, today we are going to see the topic on line coding. So line coding techniques, there are various flavors of line coding. Basically we have unipolar, polar, bipolar, multi-level and multi-transition. So we know what is line coding. So line coding is basically the conversion of the data into signals. We know the data in the computer network will be basically in the form of zeros and ones. So these zeros and ones will be converted into signals before transmission on the physical medium. So let us get into the first technique, which is called as unipolar. We'll be focusing basically on unipolar and polar techniques. So coming to unipolar technique. So all the signal levels will be on one side of the time axis, and a bit position of 1 will be represented by a positive voltage and a bit 0 will be represented by a negative voltage. So non-return to 0 is one example of the unipolar technique. So this scheme is basically prone to baseline wandering and DC component. It is not having any synchronization or any error detection techniques. It is a simple technique, but it consumes more power. So getting into the diagrammatic representation of how the bits can be converted into signals, as we have seen in the previous slide. So for example, there is a bit 0, 1, 0, 0, 1, 1, 1, 0. So we told 0 will be represented by a negative voltage, okay, and 1 is represented by a positive voltage. Again there are two zeros, so it will be continuously in the negative voltage. Now there are three ones, it will be in the continuous positive voltage, and again 0 will be in the negative voltage. So this is how you convert the bits into signals, and these signals will be transmitted via the medium. So now let us get into the next technique, which is called as your polar encoding techniques. So polar encoding techniques basically comes in three flavors. One is called as your non-return to zero, return to zero, and biphase encoding techniques. So non-return to zero basically has two flavors. One is called as your non-return to zero L and non-return to zero I. Non-return to zero L stands for your non-return to zero level, and non-return to zero I stands for your inversion. So likewise in your biphase also we are having two flavors. One is called as your Manchester and the other one is called as your differential Manchester encoding. So now let us look into one technique. So the first technique that we are going to see is called as non-return to zero. So non-return to zero means here the voltages will be on both sides of the time axis. So it can be implemented with two voltages. 0 will be represented by a positive voltage and 1 will be represented by a negative voltage. So in the next slide we are having the diagrammatic representation of these polar non-return to 0 L and non-return to 0 I. So a non-return to 0 level, which is called as L, it is represented as positive voltage for one symbol and it is represented as a negative voltage for the other symbol. Coming to the non-return to 0 inversion, a non-return to 0 inversion, it is basically the change of polarity will happen whenever we are getting a 1, and whenever there is a 0, it will not invert the polarity. So now let us look into the diagrammatic representation of how it is converted. So coming to the diagrammatic representation, so first we are going to see non-return to 0 L. So for example, there is a bit position like 0, 1, 0, 0, 1, 0. So as we have told in the previous slide, a 0 is represented as a positive voltage, 1 is represented as a negative voltage, again 0, 0, so it is represented as a positive voltage, again there are 3 ones, it is represented as a negative voltage, so you get this, so you see the signal in the lower axis, and then we are having 1 which is again a positive voltage. So it is how you can convert the bits into non-return to 0 L, which is nothing but level. Level means there are only two levels, positive and negative voltages. So coming to the next type of inversion technique, which is called as non-return to 0 I. I stands for your inversion. So in this bit position, whenever there is the next bit is 0, there will be no inversion happening in the signals. But wherever there is a next bit is 1, there is an inversion happening. So for example, let us look into the diagram and try to understand how this inversion happens. So first there is a voltage, there is a bit called as 0. So 0 stands for a positive voltage. So we have drawn the positive voltage. But looking at the next bit is 1. So whenever there is a 1, there will be a inversion. Okay, so 1, it is converted as a negative voltage. Okay, again there is 0. 0 means we know it is a positive voltage, but here whenever the next bit is 0, you will not do any inversion. It will be continuously represented in the same voltage level. Again there is 1, so 1 means there will be an inversion. So from the lower voltage you go to the higher voltage. Again there is a 1 from high to low. Again there is a 1, we go from low to high voltage. Again there is 0, so since it is already in high voltage, it will be in the high voltage only. So this is how you represent the bits in the non-return to 0 I. I stands for your inversion. So now let us get into the next technique, which is called as polar return to 0. So a polar return to 0, it basically uses three different types of voltages. One is called as your positive, 0 and negative. Each symbol will be having a transition in the middle, either from high to low or from low to 0. Okay, so the scheme has more signals, like there are two per symbol, and therefore it requires a wider bandwidth. It is not having DC component or any baseline wandering. It is not synchronized, and it is complex. Why? Because it is using three voltage levels, so it has no error detection capability too. So now let us look at the diagrammatic representation of how this polar return to 0 scheme is converted. For example, we are having the bits 0, 1, 0, 0, 1. So we have told 0 will be represented as a negative voltage, so it will be returning to 0, and 1 will be representing like from a positive voltage to 0. So it will be converted like this. Again 0, negative to 0. Again 0, it will be negative to 0, 1, positive to 0. So this is how you convert the bits to signals in case if it is a polar return to 0 scheme. So coming to the next type of technique, which is called as your polar biphase, which is called as your Manchester and differential Manchester encoding. So Manchester encoding, basically it is a combination of non-return to 0 L and return to 0 scheme. So every symbol will be having a level transition in the middle, either from high to low or low to high, and basically it is using only two voltage levels. So coming to the next technique, which is called as your differential Manchester encoding. It is a combination of non-return to 0 I stands for inversion, and your return to 0 scheme. So every symbol will be having a level transition in the middle, but the level at the beginning of the symbol is determined by the symbol value. And one symbol will be causing a level change, the other will not. So we will see how it can be represented. So coming to the diagrammatic representation of your Manchester and differential Manchester schemes. So for example, there is a bit position. So the bits are 0, 1, 0, 0, 1, 1. So in Manchester encoding, as we have already seen in the previous slide, a 0 will be represented by a high to low voltage, and 1 is represented as a low to high voltage. So let us look at the first bit. It is 0. 0 is represented as high to low. So there is a mid-bit transition happening in Manchester encoding. So if you look at the bit position 0, in the middle of 0 itself there will be a transition happening. So a 0 is represented by a high to low. So a 0 can be drawn as high to low. Then 1 is low to high. So here you can see it is low to high. Again 0, high to low. Again 0, high to low. Again it is 1, it is low to high. Again 1, low to high. And then you can draw these lines. So this is how you do the Manchester encoding. So coming to differential Manchester encoding. So differential Manchester encoding also, it is similar to your Manchester encoding, but the only thing is there will be no inversion if the next bit is 1. But an inversion will happen if the next bit is 0. So next bit is 0 means always it will touch this axis. So first, for example, it is 0. So a 0 will be having, if the next bit is 0, there is an inversion. So already we assume that there is an inversion happening in 0 over here. Then 1 will be represented as a high to low. Again it is 0. 0 means there will be an inversion happening in 0. Okay. Again there is 0. Again we assume that there is an inversion happening in 0. 1. It is just, it will be in the same state. So it is low to high. If it is in high, it will be from high to low. So this is how you do the bit conversion to signals. In the case of it is a differential Manchester encoding. Thank you.